Hi there. So, right now we're going to talk about section 2.3, which is about piecewise defined functions. Regarding this section, we haven't built up a huge cache of functions at this point. So we're not going to be able to graph a lot of very interesting things. So bear with me. We'll do what we can with what we've established so far. As the name implies with piecewise defined functions, functions can be defined in pieces, and so what we need to do is look at them in that way. So 2.3, piecewise defined functions. So what I'm going to do is take us through about 4 or 5 different examples of graphing piecewise defined functions, and then we'll do a word problem, of course, because word problems are fun. All right, so let me just show you an example right from the get-go about what a piecewise defined function can look like. So, here we are. Notice this is our function. It's defined in 2 pieces. So essentially what we're saying is for values of x less than or equal to 0, our function is x minus 2, which hopefully you're all familiar with. It's a line with slope equal to 1 and y-intercept of negative 2. Now, for values of x greater than 0, our function is simply f of x equals 5. And if that looks kind of funky to you, think of it as y equals 5. And remember what type of line that is. That's a line with slope equal to 0, y-intercept of 5, or maybe you recall that when you just have y equals, that's a horizontal line. So what I would like us to do right now is graph this line and then just play around with it, okay? This portion here is the domain portion. So this is what you look for, well, where on our coordinate system will we actually graph x minus 2? Well, we'll do that for x less than or equal to 0. Now, I always start at that endpoint here at 0. Do you agree that for x equals 0, well, I would get negative 2? Okay, now another value that I'm going to plug in is going to be, it really doesn't matter, we could plug in, say, negative 1. Notice the only values that we're plugging in are those for x less than 0. And hopefully you agree that if we plug in negative 1, we get negative 1 minus 2, which is negative 3. Okay, you can play connect the dots, and there's our line. Okay? Now, that's part of our graph. We have to do the other part. Notice the other part is for x strictly greater than 0. This is still my starting point. So I'll still say, hey, when we get super duper duper close to 0 on the right, we're going to be at 5. Okay, now since it's a strict inequality, we put an open circle there, and then the line y equals 5 looks like this. A couple things that I would like to point out to you. Okay, notice we have to put an open circle here precisely because we're interested when we get super close to 0, but not actually equal to 0. And it would be extremely problematic if we actually had this with an equal to. The reason why is then we would actually be coloring this in, but there's a problem. I claim if we actually had the equal to in both places, we wouldn't have a function. Notice at 0, it would not pass my vertical line test. So it's really crucial that you remember to put an open circle. Okay, so you color in the circle when there's the equal to, and you have an open circle when it's your strict inequality. Okay, so that's our first piecewise defined function. All right, let's do another piecewise defined function. What if now I wanted to graph this guy? Let me just erase this. And then we're also going to play with it a little bit. Suppose now we're going to actually have this graphed in 3 pieces. Okay, -2 to x less than 2 and x greater than or equal to 2. Okay, now before we actually graph this function, let's play around with another type of question that can be asked. What if I wanted us, say, to find the values of, who cares, f of 5, f of 2, f of 0, f of -2, and f of -4. I think that's sufficient. Okay? In other words, what we want to do is find the value of this function first at x equals 5. Now, this is where the domain is very relevant. We've got f of x to be defined in 3 different ways. And we have to figure out, wow, which function do we actually plug it into? Well, let's start here with f of 5. Okay, the way you know is, well, where does 5 fit in with these domains? And I think you'll grant me that 5 is greater than or equal to 2, which tells us, oh, plug it in the bottom function, and we're going to get -1. Okay? Next, where do we plug in x equals 2? Well, let's check this out. 2 is certainly not less than or equal to -2, so we're not going to plug it in the top guy. Notice we have a 2 here, but it's a strict inequality, so we're not going to go here. I think you'll grant me that 2 is greater than or equal to 2 because we have that equality. So we'll plug it in our bottom function, and we'll get 2. All right, well, where does 0 fit in here? I think you'd agree 0 is between -2 and +2, and this is a constant function, so we get 2 again. Next, if we want to plug in -2, well, we see a -2 here, but we don't have the equal sign, so what we're going to do is say, -2 is certainly equal to -2. We'll plug it in our top function. So we'll get -2 plus 4, which is 2. I think the number of the day is 2 right now. And last but not least, where do we plug in -4? Well, -4 fits in my domain here. So we'll say that's -4 plus 4, which is 0. So if you're asked to find function values, the key thing to remember is you've got to figure out which of the part of the function you're going to plug them into. All right, so let's graph this guy. Okay, first I'll start here. -2 is a really relevant number, as is x equals +2. So when x is less than or equal to -2, my function is defined to be x plus 4. Okay? Again, even if I didn't have this equal sign, I would still start here. Okay? Because that would be where I would put an open circle. In this case, we have the equals, so we can put a closed circle. So I'll start at -2, and we saw that when we plug in x equals -2, a +2 comes out. All right, if I plug in -3, well, -3 plus 4 is a +1. So I can connect the dots, and there's this part of the function. All right, Now, we're given that when x is strictly between -2 and +2, we've got a horizontal line at 2, which is really cool because check this out. Normally, we would say, oh, we got to put an open circle here and here. But notice our function actually met each other. I love when that happens. All right. And now, for x greater than or equal to 2, we've got our function to be defined as 4 minus x. Well, we see if we plug 2 in, 2 came out. So we get to color in our circle. How very exciting. All right, and if I plug in x equals 3, well, 4 minus 3 is 1. And there we have it. So while this is defined in pieces, notice it's all connected. Okay, it's continuous, which is a really neat little thing. All right. So let's play with, how about we do, let's go backwards. Check this out. Now what I'm going to do is I'm going to actually give us a graph and we have to write the formula for the function. Okay, so let us suppose this is our graph. This is the ordered pair 3, 2, and then we're at 1, 4. And then here we'll have a closed circle. And suppose we're at 3, 0.5. Well, that's not very pretty. And then 5, 1.5. And this is an arrow. Notice we have 2 lines. Notice we have a closed circle here and an open circle here, which says, yes, we do have a function. Because again, if they were both closed circles, this wouldn't pass our vertical line test. So, essentially, the way I would write this out is as follows. Okay, we know we have a function and it's going to be, in this case, defined in 2 parts because we have 2 lines. Okay, so first what I would indicate is what my domain is. Notice for this portion of the function, it's defined for x equal to 3 and then it continues on. So we can say that's for x greater than or equal to 3. And then notice this portion of our function is defined for when x is strictly less than 3. Okay, so you have to identify the domain on those graphs. Next, what we need to do is find the equation of 2 lines. Well, this is a really nice review for us. Let's find the equation of this bottom line first. Okay, remember the first thing we need to do is find the slope of the line. So the slope is the change in our y values over the change in our x values. 1.5 minus 0.5 is 1. So we get a slope of 1/2. All right. Now we can plug it in either into y equals mx plus b or the y minus y1 equals m times x minus x1. Again, it's your preference. I'm going to use the y minus y1 just because I like it. So how about we have y minus, I'll use this ordered pair, 0.5 equals 1/2 times x minus 3. So I distribute my 1/2 and I'm going to get 1/2 x minus 3/2. And in order to keep things consistent, since we have a decimal right there, we'll have 1/2 x minus, I'm usually a fraction person more than a decimal person, but Anyway, we'll add 0.5 to both sides. So we'll get y equals 1/2 x, well, minus 1. And there we go. We've defined half of our function. Now we get to do the other half. So again, we need to follow the same rules here. We first need to find our slope. Our slope is our change in y values over the change in x values. 4 minus 2 is 2. 1 minus 3 is negative 2. So we have a slope of negative 1. And just to try to keep all of you guys happy, how about we find the equation of this line using y equals mx plus b? Okay, I'll walk on over here and do that. Okay, again, it doesn't matter which ordered pair we use. I'll use 3, 2 for no good reason. So y is 2 equals m, which is negative 1. X is 3 plus b. So I get 2 is negative 3 plus b, so b is 5. Therefore, the equation of my line is negative x plus 5. Notice my slopes are consistent with the way my lines look. This has a negative slope, and sure enough, my line is going in the downward direction. And the bottom line has a positive slope, and notice it's going up in the positive direction. So at this point, we can kind of go both ways as long as they're functions that we know how to deal with already. All right, next, let's do this. This is actually the last example we need to do in this section, and it's a word problem. All right, so this next example is in the book and it's number 24, but I'll write down all of our relevant information. It says a floor refinishing company charges $1.83 per square foot to strip and refinish a tile floor for up to 1,000 square feet. So up to 1,000 square feet. There is an additional charge of $350 for toxic waste disposal for any job that includes more than 150 square feet of tile. So for more than 150 square feet of tile. And this is for toxic waste. Okay? So what we want to do is express y, which is the cost, as a function of x. So y is the cost to refinish as a function of x, which is the number of square feet that is to be refinished. Okay? So essentially, we want to write this as a function. I claim this is a classic example of a function defined in pieces. Okay? Notice for up to 1,000 square feet, which certainly includes this, it's $1.83 per square foot. And then once it's greater than 150 square feet, they have another charge of $350. So when we're less than 150 square feet, we don't have to worry about this toxic waste charge. Okay? The only time we have to start worrying about this toxic waste charge is once we get larger than 150 square feet. Okay? So my first domain area is going to be for x between 0, and 150 inclusive, okay? This is for more than 150 square feet. And I claim our function is 1.83x. Why? Because I think you'll grant me that the total charge is $1.83 per square foot times the number of square feet we need done. Now, when does the price change? The price changes once we're more than 150 square feet. But notice this whole pricing is when we're dealing with less than or equal to 1,000 square feet. Okay? And it's kind of questionable whether or not we would put an equal sign here. The way it's worded for up to 1,000 square feet, I probably wouldn't put it. I would probably put the equal sign if it said up to and including 1,000 square feet. But what's the difference in our function here? Well, it's $1.83 per square feet times the number of square feet, plus we got our toxic waste charge. All right. So, actually, I did, while doing this, think of one more function I would like to graph. Okay? But this pretty much completes the section. There's just one more piecewise defined function that I think is really important to graph. And let me show it to you. What I would like to graph is our absolute value function. Now, you may look at that and say, well, wait a minute, that's not defined in pieces, but it is, okay? Remember, when you take the absolute value of a number, you're talking about its distance to 0 on the number line. And you want to think of distance always as positive, okay? So, one way we could graph this function without even thinking about it as a piecewise defined function is as follows. We could make our handy little t-table. We could plug in values. For example, if I plug in 0, well, how far is 0 from 0? 0. Okay. What's the absolute value of 1? I claim that's simply 1. The absolute value of 2 is 2. Okay. It's just how many jumps you have to get from that point to 0 on your number line. What about -1? Well, the absolute value of -1, how far is -1 from 0? I claim it's just 1. Remember, the absolute value of any positive number is itself. The absolute value of any negative number is just the opposite. So if we were to graph this, you'll see that we get our nice V-shaped line here. But notice, couldn't we write this as the equation of two separate lines? In other words, when x is greater than or equal to 0, we can define it one way, and when x is less than 0, we can define it another way. Okay? For example, let's look. Do you agree on the positive portion of this line, it goes through these 2 points? I think you will agree. Notice we have our y-intercept, that's 0. Our slope we can compute, it's the change in y values over the change in x values, which is just 1. So, we just get, you could write 1x plus 0, which is simply x. Okay? Now, let's find what the equation of this line is. Well, again, it passes through 0, 0, and it passes through -1, +1. Okay? Why do I pick 0, 0 instead of -2, +2? I easily could have used this, but I note that that's my y-intercept. So once I find my slope, we have the equation of our line. Okay, the slope, it's the change in y values over the change in x values. So we get -1. So it's -x plus 0 or -x. And this is entirely consistent with the way we've just been talking about our absolute value, right? The absolute value of any positive number greater than 0, is itself. And the absolute value of any negative number is the opposite of itself. So, I just wanted to show you that because I think it's a cute little graph, and it's also a really nice piecewise defined function to look at. So that completes section 2.3.